Okay, so we're going to talk today about independent and dependent events, but before we start, can we talk really quickly just as a review from Friday, because we did a lot on Friday. We did 2 lessons on Friday. So just as a review from that, what is the difference, looking at number 9 in the rewind, between odds and probability? Like either just anything you know, how it's expressed, what it means.
Odds like it happening and it not.
Okay, so it's like a ratio of it happening versus it not happening. So in the case of the problem that we're talking about here, the 1 goes with what? The odds of what?
Not winning.
1 is winning, right? So 4 would be not winning. So then what's your total? 5. You have 5 choices. Okay, Brendan, what were you going to add? Odds are... Probability is written as a fraction. Very good. So we write probability as a fraction, whereas odds are written as a ratio using the... No? Colon. Yeah, you use the colon. So it's in favor of versus not happening. So for instance, if I said the odds of something in this, like the odds of you being a male in this room, right? What would be the first number? The odds of you being a male would be number of males. What would be the second number? Number of females or other, right? And then what would they add up to? The total number of people in the room, exactly. So they should add up to the total number of people. Whereas probability would be the number of males over what? Not over females. Probability would be over everybody, exactly. So probability is over the total, whereas odds are comparing in favor versus against. And remember that when we talked about in favor versus against, we're talking about opposites. So if we're saying things like, it is sunny out, what's the opposite of it's sunny out? Not sunny. It's not what?
Not cloudy.
It's not like cloudy or rainy, or why not though? Why does it have to be sunny, not sunny, rather than like sunny versus rainy?
Because they're all in that one category.
Because they don't all fit in that one category, right? We have days that are not sunny, but it's not raining, right? So there are days, you need it to cover everything. So you have to do like whatever it is and then not that. So what would be the opposite of sleeping? Not sleeping. Not what? Awake is not the opposite. That might be the opposite if we're talking like English class, or if you're teaching little kids what opposite means, that works. But in this case, we're talking in favor of, and then essentially just not that thing. So that's what we call the complement. Diego?
So if you're not sleeping, then what else is there besides awake?
I mean, you might not be able to come up with an example there, but the whole point is that you can't just use like what you think the opposite is. You could be in a coma, maybe. Right? Because you're not really sleeping. Like, I wouldn't describe somebody in a coma as sleep. I wouldn't be like, oh, he's sleeping. I don't know, because, like, I don't think it's really the same. Yeah, but that's not, like, again, if he's in a, like, when you go to sleep at night, is that the same as you go into a coma every night? No, it's not, because a lot of times... I agree with that, but when somebody's in a coma, their body processes don't usually work, right? Like, they need a machine to breathe for them. So we would say that that's probably a little different than sleeping, unless you go home at night and hook yourself up to, like, a respirator before you go to sleep. Probably not, right? So I would say sleeping and a coma are different. So maybe coma would fall into that. But either way, the whole point is it doesn't really matter if you can come up with an example. We just have to say like in favor of, not in favor of. And the important thing to remember is that odds are written as a ratio, so don't write those as a fraction. You can kind of bounce back and forth with probability between percents and fractions. That's okay. You can even write it as a decimal if you want. Okay? But when a couple people wrote 50-50, that was actually more like odds. Okay, for that first one. To write flipping one coin and having it land tails up 50-50 is really like writing odds, because it's like 50% in favor of tail, or in favor of tails, yeah, 50% in favor of heads, okay? So just be really careful with that. All right, so a teacher gives a list of book titles and asks each student to choose 2 of them to read. Adam can read 1 title from each list, or 2 titles from the same list. Hang on 1 second, guys. Just kidding. Okay. So Adam can read 1 title from each list or 2 titles from the same list. So we're going to talk today about what it means to be an independent versus dependent. So if you were to tell me what those words mean, what would you tell me? Alone, okay. Independent means alone. All right. Dependent means you rely on something else. Exactly. So independent versus dependent events in probability mean one of them depends on something else, the other one does not. So if it's an independent event, that means the results of that event are not affected by whatever the other event is. So let's say, for instance, you had a spinner and it had red, blue, green, and yellow. If you spun it once and then spun it again, is the second time affected by your first spin? No, because you could get red both times, right? Okay, so that would be independent. Whereas dependent would be something like, you have a hat with everyone's name in it. I pick out a name and I throw it away. And when I pick out another name, is that affected by what I threw out?
No.
Yes, because all of a sudden, like, let's say, for instance, I have a hat with everybody's name in it. I reach in and I pull out George. And I call on you to do whatever it is, all right, to win $1 million, all right? And then I would throw it away. If I reach into that hat again, what's different? I can't get George, exactly. So that would be dependent because the results of the second one change based on whatever you did in the first event. What if I put George's name back? That's back to independent because if I have everyone's name in it, I pull out George and then I put it back, then I still have what? Everybody's name in it, right? So it's the same exact event. It's not affected by the first one. So independent is unaffected. Dependent is affected. So in this instance, Adam can choose either 2 from the different lists or 2 from the same list. Which of these would be an independent event and which would be a dependent event? So in the first one, he's choosing a title from each list. So would this be independent or dependent? It's independent because if he chooses Animal Farm, does that affect what he can choose for his second book? No. But if he chooses Animal Farm over here, what happens when he chooses the second book?
He can't choose that.
He can't choose Animal Farm again. So now here, how many choices does he have?
4.
In the first time?
Oh,
5. Here, how many does he have?
4.
Only 4 because why? Animal Farm's gone. What about this first list? How many choices does he have here? How many here? 5. So those are independent events because nothing changes. He still has the same choices after he makes the first choice. Whereas here, once he takes out Animal Farm, he can't choose it again. So that means that it's a dependent event because whatever he does the second time is affected by what he did the first time. Okay, so we call an event independent if the occurrence of one does not affect the probability of another. So for example, rolling a die, and then rolling another die. Why would that be an independent event? It's 2 separate things. Could you roll one dice and get a 2 and roll the next dice and get a 2 again? Yes. It's not like when you get a 2, you scratch it off the die and can't roll it again, right? So it's independent because it doesn't change based on what you did the last time. Rodrigo?
Why do you put a die now instead of the dice?
Well, because
Dice is
technically dice is plural.
Well, everyone says dice.
I know. Some people have a problem with it. And I appreciate that we should be technically correct. So it should be die. I just don't like die because it sounds sad. So, all right. Okay, events are dependent if the occurrence of one does not, if the occurrence of one does affect the other. This should not say not. So on your slides, cross this out. This should say does affect. All right, so pulling a name from a hat and then pulling another is dependent because if I take the name out, then that means that I cannot pull it the second time. Okay, what do you think about A? A dime lands head up and a nickel lands head up.
Independent.
Independent, why?
2 different.
2 different coins, 2 different things. They don't affect each other at all. Okay, letter B. You choose a colored game piece in a board game and then your sister picks another color.
Dependent.
Why is that dependent?
Taking a part out.
You're taking a part out. So picture, what's a board game that has pieces?
Monopoly.
Monopoly. So they're not colors, right? But like whoever, let's say, does anyone have a lot of siblings?
I have 3.
Diego, how many siblings do you have?
4.
Okay, so let's say you're sitting down to play Monopoly at home, and you get to pick the first piece. Have you ever played Monopoly? Okay, what do you pick? You pick the dog? Okay, so then what happens for his 3 siblings? They cannot choose the dog. Why not? Diego already has it, and there's only one dog, right? So Michelangelo's going to have to do what? Play with like the top hat, right? And then your other two siblings. And then as you go down the list, each person has what? Fewer and fewer choices. Okay, so those are dependent because it depends on what the person ahead of you did before. Okay, so we talked on Friday about this thing. What is this called again? It's called a tree diagram. What is this tree diagram illustrating? The choices you have when what happens? What's happening in this tree diagram? A coin flip, right? How many times do you flip the coin? There's 2 coin flips here. So this would be your what? Sample space. What's a sample space?
Like the options.
All the options you have, right? And what do these abbreviations mean? What does HH mean? Heads, heads. That means when you flipped both the coins, you got what both times? Heads. What about this one? Heads first, then tails. What about this one? Then heads. And this last one? Tails, tails, right? So the probability of both coins landing on tails is 1 out of 4. How would I write that? 1 over 4 because it's a probability. 1 over 4, or how else? 25%. Thanks, Montreal. So those 2 options, okay? What are the odds of getting tails twice? What are the odds of getting tails both times? 1 to 3. So the odds would be 1 to 3 of getting tails twice. Why? How many options? No, you're flipping twice.
You have 2 options?
How many options are there where you get tails twice? 1. How many options are there where you don't get tails twice? 3. So the odds would be 1 to 3. Okay?
Can we try that out right now?
What?
Can we try that out right now?
We could, except that changes it from theoretical probability to what? Experimental probability. And is that going to be the same?
No.
No. Should it be close to it? Yes, especially the more times you do it, it should get close to it. But again, this is all we're talking about here is theoretical probability, because this means what basically should happen in theory. Experimental probability means what? If you actually do it, what happens in real life. And again, sometimes it's not perfect, but the longer you do it, if you do that experiment twice, it might not be perfect. If you do it 1,000 times, you should get closer to these ratios. Okay? What is the probability of flipping heads at least 1 time? What is the probability of flipping heads at least 1 time? I agree with the 3, but we're talking probability here. So 3 over 4. And then the odds, Ash, would be what? 3 to 1. Very good. The odds are 3 to 1 because the odds should add up to what? 4. Because you have 4 in your sample space. And again, sample space is just a list of all your options. Okay? You will not have to make tree diagrams that are much bigger than that, but think back to the one we did with the subway example on Friday. Okay? They can get really big. Right, and if you actually did what really happens at Subway, how big would that tree diagram get? It'd be huge, right? Because there's so many lettuce options. Okay. So to find the probability of independent events, we multiply the probability of the 2 events. So that means if you say, I want to do an experiment, I want to flip a coin 3 times, what are the odds that I end up, or what is the probability that I end up flipping heads every time? You multiply the 2 probabilities. So the way this is written is like this, where P stands for just probability. So the probability of A happening times the probability of B happening, where A and B are just your 2 separate experiments. So in letter A, an experiment consists of randomly selecting a marble from a bag, replacing it, and then selecting another marble. This replacing it means that it's an independent event. Why? You're putting it back, which means what? The first time you pick and the second time, do your options change?
Yeah.
If you put it back in the bag.
Oh,
No, they don't change. So that's an independent event. Okay, the bag contains 7 blue marbles and 3 yellow marbles. What's the probability of selecting a yellow marble and then a blue marble? So how would we do this? The probability of selecting a yellow marble and then a blue.
10 and 3.
I agree with the 10. So the 3 out of 10 is for which one?
For the yellow.
Yellow? And what's the blue?
The 7.
7 out of 10. And what do you do with those two numbers? Multiply them, because that's what the rule is. So the probability of that event happening is you multiply those two events. So this is event A, the yellow marble, and this is event B, the blue marble. Rodrigo, where did you get those fractions from?
The 10, I got it from adding 7.
Yeah, the 10 was just the total number of marbles in the bag. And so yellow was 3 out of 10 because there were 3 yellow. And blue was 7 out of 10 because there were 7 blue. But either way, they both have to be over 10 because how many marbles are in the bag? 10. All right, what would this give you? 21 over, no, 100. All right, which means if you did this experiment 100 times, how many times would you get a yellow first, then a blue? Roughly 21. All right, is that perfect? No, it might not happen perfectly, but that's what it should tend towards over time. Okay, so you're multiplying the probabilities of the A happening and the B happening, and whatever you get, that's the probability of both of those things happening. All right, when a person yeah, Brendan. Has to be 2 independent events. We're going to talk about if they're not in a second. Okay? Has to be 2 independent events. When a person rolls 2 dice and they land showing the same number, we say the person rolled doubles. What is the probability of rolling doubles 3 times in a row? How would you do this?
36.
How would you do this?
Oh, you would, so the way you would do it is you do 2 dice
Okay.
and like the tree diagram.
Okay, so we're going to set up a tree diagram where, what are the options on the first dice? First die. 1 through 6. Okay, what are the options on the second die? Same thing, but how many times do I need to write that? Yeah. I'm feeling a little bit lazy, so we're just going to make the sample space assuming that this would all be the same. So what's your first choice? 1, 1. Then I would get, then, good. Does this mean 12? No, what does it mean?
1 and 2.
You rolled 1 and then you rolled a 2. What are my
Isn't
next
that doubles, right?
So hang on one second. So what's my next option? I want to do my sample space first. 2, 1, 2, 2. My next option?
3, 1, 3, 2, 3, 4, 3, 5, 3, 6.
Again, this isn't 36, right? What does it mean? You rolled a 3, then a 6. Okay, what next?
4, 1, 4, 2, 4, 3, 4, 4, 5, 4, 5, 4, 6. 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 6, 1, 6, 3, 6, 2, 6, 5, 6, 2.
All right. Okay. Lots of options, right? But Brendan, let's go back to what you said when we made our first list. What did you say?
I said you circle all the doubles.
Yeah, so now we go through and circle all the doubles. Where are my doubles? 1, 1.
2, 2. 6,
Okay, so what is the probability then of rolling doubles?
6 out of all of them.
6 out of all of those, which, how many lists do I have? How many are in each list? 6, so altogether, so we have 6 out of 36, which I'm going to reduce because that'll make our lives easier. So divide both by 6, what do you get? 1 out of 6. So the probability of doing it once is 1 out of 6. What's then the probability if I roll 3 times? So what do I have to do to figure that out? We're almost done, I swear.
Make the tree diagram 3 times.
No, I don't need to make another tree diagram because I already know the probability of the event happening. Is it 1/6 of happening the first time, right? What's the probability it happens the second time in a row?
Multiply.
Multiply 1 over 6 times,
3.
not times 3,
3 over 1.
1 over 6 times 1 over 6. Because it's the probability every time. But how many times am I trying to do it? 3. Okay? So, what do I get? What's on top? 1. And then what's 6 times 6?
36.
And then I got to do 36 times 6. which is 216. So would you say the probability is high or low? That is extremely unlikely. So we were talking about casinos, right? Okay, so would a casino want you to try to do this? Yes, because what is the likelihood that you actually will get it? Like 1 in 216, right? Which means 216 people could try this, and how many people would actually get it? Only 1. And that's not experimental, right? That's theoretical, so it's possible that that wouldn't happen. Okay, so walk me through what we did, because that was a lot of stuff. What was the first thing we did? Tree diagram to do what? To figure out what the probability actually is, right? And once you have that, then why did we multiply it 3 times?
We wrote 3 times.
To see if you could get it to happen 3 times. Good. Okay, nice job. All right, so go try these 4. All right, so how do we do number 3? How do you do number 3? A number cube is rolled 3 times, and you're trying to figure out what the probability of rolling a 2 is each time. So what do you do here, Rodrigo? 1 over 6 is what? The probability of landing on a 2 is 1 over 6. Okay, then what do? You put another one for the second roll, because the probability is still the same, right? You're still 1 out of 6. And then another one for the third roll. So then that ends up giving you... Good, 1 over 216. Okay, so again, are those probabilities the probability high or low? Low that you will get 2 in a row every time. All right, what about number 4? The multiples of 4. So first of all, you need to know what a multiple is, which most of you got your way there. Be careful, factors are different. Multiples are what? It's like the 4's times tables, right? So the 4 times tables between 4 and 40 include what? 4, 8, 12. So basically counting by 4s, how many were there? 10. So 10 out of the 40 slips of paper are multiples of 4, which reduces to what? 1/4. Okay, so if you picked just once, the probability would be 1 out of 4. But how many times are we picking? 2. So then that would be... Good, so that gives me... Good, 1 out of 16. Okay, nice job. All right, now. So, what if an experiment involves drawing marbles from a bag without replacing them, which means it's no longer independent, now it's what? Dependent? It's dependent because if you don't replace the marble, that means if you had, let's say for instance, in your first draw, how many marbles were in this bag? 9. There are 9 marbles in the bag this time. And what are the odds? Sorry, not odds. What's the probability of choosing red? 3 out of 9. Okay, what happened here? It took away a red one, and now how many marbles are there? 8. So what is the probability now of choosing a red? 2 over 8. So what happened to the probabilities? What decreased? The chance of getting it and the total, right? So the total decreased. What would have happened now if there had still been a red, but that one wasn't there? What would the probability have been here? Would have been 3 over 8. So no matter what, which one is going to decrease? The bottom, because that's your total number. Because what happened when you took the marble out? You didn't put it back, so you can't have 9 still, right? So you still multiply, but the only difference is, are they going to be the same? No, they're not going to be the same number. So the probability here is 3 out of 9. And then the probability here was 2 out of 8. So what would you end up with? 6 over 72. And can I reduce that? Yes, 6 goes into both. How many times does 6 go into 6? 1. And how many times does 6 go into 72? 12. So what's the probability you'll get reds both times? 1 out of 12. This would be red, okay? Okay, what's the probability you get blue both times? What's the probability you get blue both times? So the first one is 6 out of 9. And then the second one is 6 out of 8. And you just multiply those. So 6 times 6 is 36. And 9 times 8 is still 72. I'm going to divide by 6 again, but I'm going to get 6 out of 12. So then I can reduce that to what?
1/2.
1/2. Good. So which probability is greater? The blue one? Which makes sense. Why? There's more blue marbles. Okay? So there's more blue marbles in there. So again, how is this different than if they're independent events? If they're independent events, your fractions should be what? The same every time. If you do it 10 times, it'd be the same fraction every single time. If it's a dependent event, what should be happening to the denominator? Decreasing. Good. Very good. Okay, so then one more, the last one, is what about red first, blue second? All right, so what about red first? What would be the probability of red first? 3, 9. And blue second? 6, 8. And what would you do with those? Multiply. So you get
27. Wait, my bad.
18. Good. Which I'm going to divide by 9, which is 2 over 8, which is 1 over 4. Okay? So which of these is the lowest probability? Red both times. All right, red both times is the lowest probability. Why is this one smaller when 12 is bigger than 4? How come the probability of this one is actually less than the probability of this one? Because the number is bigger.
I learned this in like 3rd grade, but I couldn't forget.
Yeah, like how come 1/12 is smaller than 1/4?
It's like one is you actually getting it, or is you not?
Okay.
It's actually worse to have a 12 than you not get it.
Okay. As in all things, I like to think about it in terms of food. If you have a pizza and you cut it into 12 pieces, they're smaller slices than if you have a pizza and you cut it into 4. So if you have a pizza and you cut it into 4 and I give you 1 piece, that's a pretty good piece, right? But if I take that same pizza and cut it into 12 and then give you 1, Angel, then did you guys get the same size piece? No. Like, I'll be like, well, I gave you both 1 piece of pizza, but Angel would be mad, right? Because his piece would be a dinky little slice. It'd be like a freshman retreat when everyone was like, I don't want that little bitty piece when I could have the huge one, right? So when you think about fractions, even though 12 is technically a bigger number, because it's in the denominator, that's how many slices you have, so the slice is actually smaller. Okay. All right, the probability of choosing a red card from a standard deck of playing cards is 50%. What are the odds of choosing a red card? What are the odds of choosing a red card? So think back, what's odds mean again? Blank to blank, where the first blank is the odds of red, right? It's 1/2. It's all, and not quite. I agree that that's the probability. I agree the probability would be 1/2. What would the odds be? 1 to 1. Why? There's only red or black, right? So you're either going to get a red card or a black card. So it's 1 to 1. Okay. All right, we're going to skip this one. Okay, so for practice, do just, no, try them all. You have time. Try them all.